So what are the discretization difficulties associated with interface problems? What are the challenges? So first of all, we are in a case where we are evolving complex geometries. We have accurate calculations of front velocities, because if we move things forward in time, like for fracture, as we said yesterday for Griffith crack in the presentation on data-driven methods, clearly there are some issues if we are not able to do that properly. Then we need to compute the error, because if we don't compute the error, we don't know how accurate the solution is, and then we need to deal with time-stepping schemes. So let's take a very common example, which is known as fracture mechanics first. So in moving discontinuities and singularities for fracture mechanics, here is what we can think of and what is important to know. First of all, it's important to know that fracture is omnipresent, it's ubiquitous, it's everywhere. You can look at the shuttle crash in 2003, the landslide in Colorado, fragmentation of concrete, Taiwan earthquake. You name it, there are fractures everywhere, and sometimes even they are desired in order to reach the target that you want. For example, for fracking, you try to create fractures in order to extract shale gas. So you know that some aircraft, as the Comet aircraft, became, let's say, convertible, but that was not foreseen by the designer, and that was because the windows were square, and of course that led to fracture and coalescence of the cracks, which led to rupture of the fuselage. Fortunately, the casualties were very limited in this crash. Finally, as we were saying, oil extraction from shale requires cracking, so you have some pre-existing faults, and the idea in these simulations that we did when I was at Cardiff and published in SPE is basically to look at how to extract shale gas from shale, which is a nanoporous rock. So again, here you're trying to figure out how to use the cracks to your advantage and to create other cracks if needed. Composite materials are materials which will contain cracks. So for example, here we have a unidirectional composite where the fibers are running in this direction parallel to the fracture that you see. And this is the thesis of Lisa Cahill in Limerick, and what we saw is that we were able to replicate with a very, very simple XFEM model, extended finite element model, the direction of the crack in this anisotropic material. So you see the experiment here and the numerics here. Of course, it was a very simple fracture pattern, but we replicate that with Mao Sheng in the US and in China, where he did some experiments. Where we have some hydraulic fracturing in the rock, and the goal was to look at the propagation of the cracks. So we have a series of papers on hydraulic fracturing and shale gas and other areas which we could talk about if you're interested. And finally, fracture in aerospace components. This is in collaboration with my friends at Senairo in Belgium, and not far from here in Luxembourg. Where we look at 3D fractures with error estimates. So you see here, this is a very interesting problem because the crack is propagating, and if you have an incorrect measure of the stresses and the stress intensity factors, you see that erroneously the crack merges with the hole instead of avoiding the hole. And it is quite a difficult problem because the crack is 3D, so it just glazes off the interior here of the hole, but does not stop there. It continues, it deflects. And this is very hard to find if the error estimate that you have is not precise enough. And finally, we talked also about mesh-free methods for cohesive, quasi-static crack growth, and this is something which we worked on with Timon Rapsuk using elementary Galerkin with or without enrichment. So these papers are from 2007. They are highly cited now, and you can take a look at them if you're interested. Now, how do we handle fracture of homogeneous materials? So essentially, the question is, if you have a structure, you would like to know when it should be inspected for flaws. Why? Because most aerospace structures are allowed to be defective. So they are allowed to have flaws and fractures that propagate, as long as we know how fast the fractures propagate. If this is the case, we can leave the fractures in the components. It's okay. It's called damage tolerant design. And the reason why we can leave them there is because we know that during a certain amount of time, during a certain number of takeoffs and landing, for example, we know that the cracks will propagate a certain amount, but not more. So we are able to control the amount of propagation between two time intervals, between two inspections, and therefore we are able to control the inspection intervals, and that's very important. So this was talked about in my first PhD paper in 2006 and 2007. And I think it's very important, and we continued working on this for industrial applications in 2008, and most recently in 2020 we have the full-blown error estimate approach for 3D fractures using finite elements and extended finite elements, and I think it's a beautiful paper. Okay, so what are the most pressing issues in computational fractures? So first of all, we need to figure out what are the model choices. Why? Because as we know, we could discuss small-scale yielding, meaning that the fractures are, let's say, relatively small, and the damage or plastic size is very small compared to the crack size. So that could be linear elastic fracture. But we could have elastic plastic fracture where the plastic zone is much larger than in the case of elastic fracture. Finally, we could decide about damage models that are local, non-local, or gradient-based, or we could work on multi-scale approaches. And these multi-scale approaches, as we will see, are both either concurrent or semi-concurrent or adaptive. And this is something we'll talk about. Discretization choice, how do we select the discretization we need? So are we going to find from finite elements, which we know has problem with remeshing, for boundary elements, which cannot handle nonlinearities very well, for extended finite elements, which we know has difficulties for multiple cracks, or for mesh-free methods, which we know has difficulties about cost, stability, and robustness. So all these things are not trivial, and it's important to think about these questions before we go and we embark into choosing an approach. So one approach that we used here in my group, in the Legato team at the University of Luxembourg, is the Phoenix project, which you can see here, the logo of. And the idea is to implement high-level descriptions of finite element models in a unified form language. So the idea is that you start from something written by hand. You can write the strong form, and from the strong form, the weak form will automatically be derived once you have set up exactly what approximation spaces you want. And then you let algorithms take over the work of linearization, transforming math into lower-level languages that are used at the computer level. And this is very difficult to do, and it scales to really huge problems with billions of unknowns on the top 100 supercomputers. So it is something very serious. And the idea is to separate the expertise of the person, so problem to mathematical model, from the algorithmic and suitable for automation, which is the linearized model, numerical model, and the software itself. So as we said at the beginning, we keep our expertise, which is setting up the problem and finding the mathematical model, and then we let the computer do the rest, which is really very efficient. If you are interested, we can discuss that. And now 6 years ago, we hosted the Phoenix conference here in Luxembourg, and you can also see details on the Phoenix project here.